Okay. Hello, everyone. Welcome to this seminar of the Astronomy Department of IAG-USP. Many thanks for your participation, if you are here in the Google Meet or in our YouTube channel. And today we have the pleasure of having with us Guilherme Limberg, that, well, you know, because he also is organizing the seminars, but today he's presenting his work. So many thanks, Guilherme, for accepting the invitation and being here.
Thank you.
Sharing your work with us. So Guilherme got a bachelor degree in astronomy at the IAG-USP, and currently he's a PhD student, a third-year PhD student here at the IAG. He works on galactic archaeology, and he's a member of the Galactic Archaeology group here at the IAG. And today, Guilherme will present Reconstructing an Ancient Dwarf Galaxy with Stars and Globular Clusters. So, as always, if you have questions, you can ask the question, raise your hand here in the Google Meet, or if you are in the YouTube, you can write it down in the chat and we will ask the question later to Guilherme. So please, during the presentation, turn off your cameras and your microphones. And well, that's all. Guilherme, whenever you are ready, you can start sharing.
Thank you, Maria Victoria.
You're welcome.
Let me just share my screen. Okay, I think everybody can see my screen. So
Yes.
Thank you, Maria Victoria. Thank you, Maria Victoria and Reinaldo, for inviting me. Every semester, the cycle of seminars is going to invite a grad student now. And I had the pleasure to be, or the honor to be invited by Reinaldo and Maria Victoria. And just like Maria Victoria told you, I am a PhD student. I am a third-year PhD student here at the Astronomy Department. My advisor is Professor Silvia, and we work in Galactic Archaeology. We are the Galactic Archaeology group, and I'm here to present to you a few results that we got trying to using stars in our Milky Way to reconstruct ancient dwarf galaxies that have been accreted throughout the history of our galaxy. So just to begin with, I would like to recall the hierarchical assembly of galaxies in general. And in this simulation that we see, we will see the formation of a Milky Way mass galaxy, a massive spiral galaxy. And throughout the simulation, we will see that this massive galaxy forming in the center of the simulation, it is growing in size. It is assembling its mass through a succession of accretion events of smaller dwarf galaxies. And the takeaway message from the simulation, or the thing that I would like to call your attention to, is that our Milky Way should be no exception to this hierarchical formation paradigm. So our Milky Way probably assemble its mass or assemble its galaxy, or the halo of our galaxy should be composed of a bunch of dwarf galaxies that have been accreted throughout the history of our galaxy. And well, the thing is, here in the picture on the right, I show to you a snapshot from a simulation from the Aquarius project, a simulation that this is a simulated halo of a massive galaxy with a mass pretty similar to the Milky Way. And you can see, and in this simulation, since we know the assembly history of this galaxy, because we are kind of in God mode, we can actually color code every single particle in the simulation according to its progenitor galaxy. So in this figure to the right, every color is a different dwarf galaxy that have been accreted throughout the history the formation of this galaxy in the simulation. So we can see that the halo of galaxies as massive as the Milky Way, they should be a complete mess. So this is basically the takeaway message. And the question that we can ask ourselves is there a way for us to color code stars in the Milky Way's halo, represented here by this artistic representation of the galaxy? Can we color code each star in the halo of our galaxy, just like we did with the simulation? And from the simulation that we just saw regarding the hierarchical assembly of a galaxy massive, such as a massive galaxy such as the Milky Way, we actually saw that these these galaxies, since they are assembled from a succession of merging events of these small dwarf galaxies, they are falling onto the galaxy from a variety of different directions with different geometric properties of their mergers. We should actually see that the motions of stars from these dwarf galaxies, they should be a complete mess as well. They should be moving in all sorts of directions, and therefore their motions should be very different from stars in the disk of our galaxy that should be rotating in a very organized way. And furthermore, the stars from these dwarf galaxies, they should have very different chemical compositions from the stars born in the Milky Way itself, because they were born in these dwarf galaxies, these systems that experience different star formation and chemical evolution histories. So taking this into consideration, I will show to you this. This is a This is just a video of a bunch of small dwarf galaxies represented here by the different colors being thrown into a galactic potential model very similar to the potential of the Milky Way. And you can see that throughout this video, throughout this simulation, these dwarf galaxies that fall into the potential of the Milky Way, they are completely disrupted. And throughout the simulation, or throughout the time of the simulation, as time passes, these stars from these dwarf galaxies, they will eventually be very well mixed within the potential of the Milky Way, within the halo of this simulated Milky Way. But despite the amount of mixing that these stars suffer, and despite the amount of phase mixing that they experience, despite being completely disrupted into the halo of the Milky Way, you can see in the right that they still maintain a certain amount of coherence in this orbital energy versus angular momentum space. So the main takeaway message from this simulation, from this small video, is that indeed we can utilize, despite phase mixing, despite how well mixed these stars are in the halo of our galaxy, we should be able to utilize the kinematics, the motions of these stars, their dynamics, in order for us to select which stars belong to the halo and which stars belong to the disk, and even to select which stars from the halo belong to each dwarf galaxy that has been accreted throughout its history. And regarding the chemistry, we can actually utilize surviving dwarf galaxy satellites of the Milky Way in order for us to explore what is the chemical composition that we should expect for accreted stars in our galaxy. And this is a plot from a paper, from a review by Tolstoy from back in 2009. And we can see that most of these dwarf galaxies, these are some of the most massive dwarf spheroidal galaxies that are satellites of the Milky Way. And we can see that overall, the dwarf galaxies, the stars from these dwarf galaxies, they are more metal poor than the bulk of the stars from the Milky Way, which are represented here by the gray dots. But the most important feature, I guess, from this figure is that independent from all values of metallicity, here represented by the ratio of Fe over H, you can see that despite, from all values of Fe on H, stars from these dwarf galaxies, they have lower abundances or lower ratios of magnesium over iron. Magnesium here are representative of alpha elements. And this is a consequence of the different chemical evolution history that these dwarf galaxies experienced. Furthermore, we can see that, for instance, the Sculptor dwarf galaxy, here represented by these pink points, or magenta or purple, I don't know, they follow a very cohesive sequence in this chemical abundance space. The abundance of the ratio of magnesium over iron, it declines with increasing metallicity in a very consistent way. So this is very characteristic of a very simple chemical evolution history experienced by this dwarf galaxy. And this is another way to see this. This is an illustration by a paper back in 2012. We can see basically what we see to the, let's see the right panel first. We can see exactly what we, this is a panel that kind of represents which kind of population we should expect in this chemical abundance space when looking at stars in the Milky Way. We can see that this region of low alpha over iron abundances, low alpha over iron ratios, is dominated by the accreted population. They are dominated by the accreted population in the Milky Way because the Milky Way should be composed by a variety of different dwarf galaxies similar to the surviving satellites that we see in the top panel. Towards high metallicities, we should see a bunch of stars from the disk of our galaxy. So these stars were born in situ within the Milky Way itself. And towards lower metallicities at high values of alpha over iron ratios, or magnesium over iron in the top panel, we can see that these populations start to kind of mix together. So this is kind of difficult to disentangle. But overall, stars that are accreted in the Milky Way, they should have low abundances of magnesium, of alpha over iron, for instance, independent for the same metallicity in comparison to the stars in the Milky Way. So this is the takeaway message. And of course, people have explored these ideas for many years now. And this is a very important paper, at least in my opinion, in which these authors, Nissen and Schuster, they analyze a bunch of stars from the halo of our Milky Way, and they know that these stars were born in the halo of, or belong to the halo of the Milky Way because they had the kinematics for these objects. And they analyzed with high resolution spectroscopy, and they derived a bunch of abundances for these objects. And we can see that overall, the halo of our galaxy, at least in the solar vicinity, all of these stars are within 300 parsec from the sun. This is a very nearby sample. The halo can be divided broadly into two populations: a high alpha population with high abundances of alpha over iron, or high alpha over iron ratios, and a low alpha population represented here by the cyan points. And one thing very important from this plot is that these yellow points, they are kind of indistinguishable from the white crosses. And these white crosses are stars from the thick disk that were analyzed in the same observational campaign. So the halo of our Milky Way is composed by these two populations. One of them has high alpha abundances, which are indistinguishable from the chemical abundances of stars from the thick disk, from the canonical thick disk. On the other hand, there is a bunch of stars with low alpha abundances that are very similar to the region of this chemical abundance plane that is indeed expected for accreted populations. And looking at the kinematics now, we can see that this yellow population, this high alpha population, it kind of constitutes kind of a continuation of the thick disk in this distribution, this velocity distribution. On the x-axis in this plot, we see a measurement of the amount of rotation that the stars have around the galaxy center, and in the vertical axis, the vectorial sum of the other components, kind of the random motions that these stars have. And we can see stars on the thick disk, they rotate in a proper direction, the same direction as the disk, of course, and then this high alpha population, it kind of constitutes kind of this dynamically hot portion of the thick disk. On the other hand, the low alpha population, most of them have either no rotation at all or almost no rotation at all. They are all around this dotted line here, or they even have retrograde motions in comparison to the disk. So they are moving on the opposite direction in comparison to the disk of our galaxy. And this is indeed what it would be expected if we have a bunch of dwarf galaxies, a bunch of accreted stars that have random motions in comparison to the disk of the Milky Way, because they fell into the galactic halo from all sorts of directions. Yeah, fast forward towards the 2018 when we had the advent. So now in 2018 we already have Gaia. So this now using Gaia data. Gaia is a satellite. We had a lot of talks here in the cycle of seminars about Gaia. Gaia is a space mission that from a satellite that observes a bunch of stars in the Milky Way. It scans the sky a lot of times, measuring colors, magnitudes, so the brightness of stars, the proper motions, and parallaxes. So with this data set, we can actually analyze the kinematics for a much larger samples of stars. And this is exactly what is shown in this figure. This is from left to right, from right to left, sorry. We have decreasing metallicities. So we have a bunch of panels of velocity distributions of stars near the, most within 3 to 5, they are within 3 to 5 kiloparsec from the galactic plane. And what we can see in these velocity distributions in the horizontal axis, we have the radial motions of stars, and in the vertical axis, we have the rotation. And what we can see is that, indeed, within the metallicity interval analyzed by Nissen and Schuster back in 2010, back in the previous slide, we can see that most of the stars, they have this behavior where they have almost no rotation at all. They have almost no rotation. On the other hand, if we go towards more metal-poor stars, we can see that this velocity distribution starts being more isotropic, kind of exactly what we would be expected for a halo of a Milky Way that would be composed by a variety of different dwarf galaxies falling from all sorts of directions. We would expect something like this isotropic distribution of velocities. However, towards, let's say, high metallicities, of course, this is already quite metal-poor, because the FE1H is -1, which is 1/10 of the metallicity of the sun. But towards this metal-rich portion of the halo, we can see that the stars, the velocity distribution of stars, is very anisotropic. So this is an indication that the metal-rich portion of the halo, or this no-rotation portion of the halo, it is composed of a different thing, something different from an accretion of a variety of different dwarf galaxies falling from random directions. And what we can see is that this sausage shape that comes, or sausage, in the words of the authors by Belokurov in 2018, and you can see that this distribution of velocities is very similar to a sausage shape. And just so you can envision what kinds of motions these stars have, in cyan here, I have the orbit of a star very typical from the sausage structure. You can see that the orbit of these stars from the sausage are very eccentric. They have very high eccentricities in comparison to stars from the metal-poor portion of the halo, which have more circular motions in comparison to the sausage portion. Okay, so what can we explain this duality in the halo is something that I will try to explore in the next slides. So then came Gaia-DR2. All of the work Paulo could have in the previous slide was done with a combination of Gaia-DR1 and SDSS, and then it came Gaia-DR2. And in this HR diagram of high velocity stars, so these high velocity stars should be all stars from the halo. They are kinematically associated with the halo. We can see in this HR diagram, just by plotting these stars in this color magnitude diagram, we can see that two sequences appear. One, a bluer sequence, and a redder sequence. They can be perhaps it's easier to see dividing them with this isochrone here. So this isochrone can divide these two populations, the blue and the red sequences. And the blue and the red sequences, people realize that these sequences actually correspond to the duality between the high alpha and the low alpha groups that I just mentioned to you from the work of Nissen and Schuster. So look at, notice that the blue sequence, the yellow points here actually correspond to this no rotation portion of the halo, this almost no rotating portion of the halo, while the red sequence actually corresponds to that continuation of the thick disk that corresponded in the work of Nissen and Schuster to the high alpha population. And indeed, this kinematic structure that was revealed with the advent of Gaia-DR2 was actually reproduced in simulations on past simulations. This is actually a simulation from back in 2010. These simulations, I think 2008 actually, these simulations were run in these simulations between mergers of Milky Way mass galaxies and dwarf galaxies were utilized in the past to study the dynamical heating of the disk from the accretion of dwarf galaxies. And from just simulations, this is not a fit. This is a pre-existing simulation. The authors noticed, these authors, especially Helmi et al. Back in 2018, they realized that the kinematic structure that we were seeing for the galactic halo with the advent of Gaia-DR2 was very, very similar, including this retrograde tail that we see in the data. And this simulation corresponds to the accretion of a single dwarf galaxy, a pretty massive dwarf galaxy, onto a Milky Way mass disk galaxy. So this was kind of the interpretation that these authors had, that this kinematic structure, this non-rotating portion of the halo, this blue sequence corresponded to the accretion of a single dwarf galaxy, a pretty massive dwarf galaxy that was accreted like 10 billion years ago or something along those lines. However, and then we can actually utilize data from other surveys, other new surveys. We can also analyze the chemistry of these objects. And this is exactly what I show in this figure. Now, I am showing to you the same division here, the same division between the blue and the red sequence. So the non-rotating and the hot disk portion of the halo, and you can see that this separation with this in this color magnitude diagram actually corresponds to a separation in chemical abundance space, and we can see again the formation or this duality between the low alpha and the high alpha populations popping in this chemical abundance space or emerging in this chemical abundance space towards low alpha magnesium over iron abundances, the low alpha population. They are more metal poor and they have almost no rotation at all, similar to the results from Nissen and Schuster. And the high alpha population is actually this hot portion of the thick disk. And then the interpretation for these results was that a major accretion event, according to the simulations, occurred in the Milky Way between 8 and 11 giga-year ago. And this was a result that was actually achieved by Belokurov, even before the advent of Gaia-DR2, and even before having the information regarding the complete chemical abundances, the complete abundance of alpha elements. So this is quite by comparing the velocity distributions that they were getting with simulations of galaxies merging. And also in this paper by Helmi et al., they actually proposed, or they saw in their simulations, that not only this galaxy was a massive accretion event that happened in the history of our galaxy, but also this massive dwarf galaxy had carried enough kinetic energy to dynamically heat a primordial disk of our galaxy, forming this other portion of the halo, the high alpha population, would be formed from the dynamical heating of the primordial disk that existed before the merger. And they refer this merging event, or this massive dwarf galaxy accreted by the Milky Way some 10 giga-year ago, as Gaia-Enceladus. So here is kind of a storyline of the Milky Way that we can kind of construct with this scenario. Before the merging event happened, before this merging with this Gaia-Enceladus galaxy happened, we had a kind of the presence of a primordial disk in the Milky Way. And then here comes this galaxy, it crashes onto the onto the Milky Way. This was probably a gas-rich merger that triggers star formation. And then after the merger, we have the formation of this heated portion of the disk, forming kind of this in situ counterpart of the halo alongside the accreted portion of the halo, and then the present day structure of the Milky Way with the halo very well mixed. All these stars from this massive accretion event, they are all mixed throughout the halo of the Milky Way. We cannot see a spatial coherence anymore. However, these stars also were, the accretion of this galaxy was broadly responsible for the formation of the halo that we observe today. And analyzing these simulations, some other authors actually were able to indeed see the presence of the sausage structure in velocity space, similar to what we see in the data. And then we can kind of establish or kind of tell the merging history of the Milky Way as a sequence of its most significant merging events that we saw that happened for the past 10 billion years. First, 10 billion years ago, there was the accretion with this Gaia-Sausage or Gaia-Enceladus galaxy, and other smaller dwarf galaxies probably were accreted before that. But this merger with this Gaia-Enceladus galaxy was the last significant accretion event experienced by the Milky Way, significant in the sense that it produced a lot of transformation in our galaxy. And the debris of this accretion event should be very well mixed with the Milky Way, as shown here by this redshift greater than 2 snapshot in the simulation of a Milky Way mass galaxy. The debris of this massive dwarf galaxy is scattered all around the halo of our Milky Way. And about 5 billion years ago, there was the accretion of the Sagittarius dwarf galaxy, which is now responsible for the production of the Sagittarius string, this string of stars that is all around the Milky Way. And this Sagittarius dwarf spheroidal, the string produced by the tidal disruption of the Sagittarius dwarf galaxy, can still be observed as a coherent with a coherent spatial distribution, as is represented by this intermediate redshift snapshot in the simulation. And the last important accretion event that happened, or that is currently happening in the Milky Way, is the infall of both Magellanic Clouds, both the small and the large Magellanic Clouds. And they are still seen as a very, very spatially coherent, as is demonstrated by the colored dots in the simulation. And so, what else should we expect from this massive merging event? So, this is a massive galaxy. This galaxy was just as massive as the Large Magellanic Cloud, or in between the small and the Large Magellanic Cloud. There is a bunch of mass estimates in the literature. This was a very massive galaxy, which has a high metallicity, or at least the metallicity of this galaxy was very high in comparison to the other stars in the halo. And we can see the kinematic or the dynamical footprint or the dynamical signature of this merging event very clear in the halo of our galaxy, from simply by plotting a color magnitude diagram of high velocity stars around the sun. We can see this population naturally appearing. So what else should we expect from a merger with such a massive galaxy such as Gaia-Enceladus? And we should also expect that this dwarf galaxy would also bring a lot of globular clusters to the Milky Way, as is represented in this simulation. To the left, I have a Milky Way mass galaxy from a simulation from the eMosaics project. This is associated with the EAGLE project for cosmological simulations. And to the right, we have an edge-on view of this galaxy, and plotted, and on top of that, the system of globular clusters associated with this galaxy. And we can see that a bunch of dwarf galaxies, or a bunch of globular clusters, are actually born within this massive spiral galaxy itself. However, a good portion of its globular clusters were actually accreted from a bunch of small dwarf galaxies. And in this bottom panels, I actually show different snapshots of this same simulation, with different redshifts, and we can see from the high redshift snapshots that the central massive dwarf galaxy, the central massive galaxy that is formed in this simulation that corresponds to the top panels, this dwarf galaxy actually experienced several merging events with other dwarf galaxies, as highlighted by the yellow circles here, which also carried a bunch of globular clusters that end up forming the globular cluster system of the massive galaxy. And indeed, people have tried to explore the system of globular clusters of the Milky Way and try to decompose these globular clusters into its various dwarf galaxies that were responsible for their accretion. And this is indeed what I'm showing in this top panel. This is again that energy angular momentum space that I showed to you in one of the first slides. And you can see in this work, the authors try to perform kind of a mixture model decomposition of the globular clusters in the Milky Way based on their dynamics. And we can see what pops out of this. The green points in this plot actually correspond to the globular clusters associated, or that these authors associated with the Gaia-Enceladus galaxy or Gaia-Sausage, whatever the name you want. And you can indeed notice that the sequence in this age-metallicity plane here in the bottom panel, you can see that indeed the globular clusters from this they were associated with this merging event. They follow an age-metallicity sequence that is very different from other globular clusters in the Milky Way. Notice this population of high metallicity, very old globular clusters here that I'm showing you with my mouse. And you can see these globular clusters are, these high metallicity, very old globular clusters are associated with either the bulge or the disk of the Milky Way. And the age-metallicity sequence followed by these globular clusters from this Gaia-Sausage or Gaia-Enceladus galaxy. They follow a very different relation in this parameter space. Okay, so what do we know about Gaia-Sausage and Enceladus? Let's summarize what we know in order for us to try and ask some questions regarding what else do we want to know. So it was a massive dwarf galaxy accreted between 8 and 11 giga-year ago, let's say 10 giga-year ago. It was as massive as, or in between the small and the large Magellanic Cloud. It is the last significant merger experienced by the Milky Way with a mass ratio between 1:3 and 1:5. It was responsible for the dynamical heating of a primordial disk. So it was broadly responsible for the formation of the thick disk and its hot component that we saw in the previous slides. It also composes most of the inner galactic halo. It composes most of the inner halo, and we know that because just by plotting a color magnitude diagram of stars in the halo, we can see this population appearing. It was also potentially a gas-rich merger that potentially triggered star formation within the Milky Way. However, this is quite difficult to explore. It also brought with this dwarf galaxy about between 20 and 30 globular clusters that now constitute the globular cluster system of our galaxy. And these globular clusters, when we segregate them from the rest of the Milky Way, we can see that they follow an age-metallicity relation, very different from the globular clusters that were born in the Milky Way itself. What else do we know about this galaxy? Is that this galaxy, or the naming for this galaxy, actually makes a lot of people mad on Twitter. Some people call the Gaia-Sausage terminology ridiculous, and you can see from this promotional figure, it's like this Greek mythological figure smashing into a spiral galaxy. And this is exactly why a lot of people utilize the combined naming. So Gaia-Sausage and Enceladus, this crazy mixture between food and Greek mythology. For instance, so some very, very important people on Twitter actually utilize this mixture of these nomenclatures. So what do we still want to know about this dwarf galaxy? One of the things that we actually want to know is how does this dwarf galaxy, how the Gaia-Sausage and Enceladus galaxy compare with surviving dwarf galaxies? And this is very difficult to do because we would need a data set that allows us to perform this comparison. For instance, what is the chemical abundances from this Gaia-Sausage and Enceladus galaxy, and how does these chemical abundances compare with surviving dwarf galaxies, satellites of the Milky Way? And it's very difficult to do because we would need a data set that both observe these dwarf galaxies and also halo stars in the field of in the Milky Way itself. And among this system of globular clusters that this galaxy brought into the Milky Way, was there any nuclear star cluster in this galaxy? This is also a question that we can ask ourselves. Looking at the globular clusters accreted within this merging event, was there any nuclear star cluster? And what is the true age-metallicity relation defined by its globular clusters? Because we actually need, in order for us to define the true age-metallicity relation, it would be necessary for us to have a data set of globular clusters with a self-consistently determined ages and metallicities. So this is all questions that we can ask. And in fact, we ended up realizing that, our group ended up realizing that we actually do have the data set necessary in order for us to answer all of these questions all at once with the same data set in a self-consistent way. We can combine data from Gaia again, of course, we utilize Gaia for everything in this field. And we can combine data from Gaia with data from Apogee. Apogee is a spectroscopic survey, a high-resolution spectroscopic survey that is conducted from both hemispheres. And this Apogee survey had sub-projects within it that actually observed a bunch of stars within globular clusters, as well as in the field, as well as in dwarf galaxies of the satellite galaxies of the Milky Way. Most important, the Apogee survey observed a bunch of stars in a bunch of globular clusters that were accreted alongside Gaia-Sausage, as well as the Apogee survey observed a bunch of stars in the small and the large Magellanic Clouds, which are the most massive dwarf galaxies, satellites of the Milky Way that actually have a mass that is very comparable to the predicted mass for the Gaia-Sausage Enceladus galaxy. So, the first thing that we did in order for us to explore all of these questions that I raised in the previous slide was to select the members of this Gaia-Sausage Enceladus dwarf galaxy. And in order for us to do that, I utilized a combination of, I utilized some kind of dynamical selection. And we saw in this figure, I'm showing the rotation. Again, this component of angular momentum that we saw in some of the first slides. And in the vertical axis, I have another component of the dynamical quantity that's kind of a proxy for orbital eccentricity. And I'm using this combination of parameters because we saw from that video that I showed a few slides ago that the stars from this Gaia-Sausage Enceladus, this metal-rich portion of the halo, they are very eccentric. So we know that we can utilize orbital eccentricity to segregate stars from this population from the rest of the stars from the Milky Way. And we can also utilize this component of angular momentum because we know from, I don't know, the first simulation that I showed to you in the second slide of the presentation that this quantity is conserved. So we can utilize a combination between them in order to select a very pure sample of stars from this dwarf galaxy within the stars in the halo of our galaxy, of the Milky Way. And then we can actually utilize a combination, given that this high-resolution spectroscopic survey, this Apogee survey, it provides a bunch of chemical abundance. We can utilize this chemical information in order for us to eliminate which stars in our dynamical selection were actually contaminants from the thick disk, for instance. And this is exactly what I'm showing in this figure. I'm using a combination of chemical abundances. Just for the reference, this is a combination between magnesium, manganese, aluminum, and iron. And this chemical abundance space was specifically designed or explored let's say, to maximize the separation between accreted and in situ populations in the Milky Way. And then what we can see is that the metallicity distribution function that we obtain, so metallicity distribution function is just a fancy name for a histogram of metallicities. The metallicity distribution of this population actually forms a very strongly peaked distribution. So, okay, this is kind of reassuring because this is exactly the behavior that we see in surviving dwarf galaxies. But okay, now we have a very pure sample of stars from this dwarf galaxy, this Gaia-Sausage galaxy, and then we can actually compare our metallicity determination for this population with others from the literature. I'm basically showing this to show that our determination is like not crazy in comparison to the literature, but one thing to notice is that this literature estimates for the metallicity actually converge to much higher values back from the original paper of the discovery of this population down to the present day. That's because we just improved our selection of member stars from this accreted dwarf galaxy. But not only that, this comes with a caveat. So this characteristic metallicity for this population actually, or this determination for the characteristic metallicity of this population actually comes with a caveat. And the caveat is that we don't exactly know what is the footprint of this dwarf galaxy in dynamical space. And this is a very important information regarding this dwarf galaxy that was accreted that I think this is the right opportunity for me to mention it, is that this is in this top panel here that I'm showing, this is a simulation. This is an any-body plus smooth particle hydrodynamics simulation of the merger between the Milky Way and this dwarf galaxy, this massive dwarf galaxy, this Gaia-Sausage. And you can see that such a massive dwarf galaxy, it is actually capable of developing an internal metallicity gradient before the merging event occurs. And therefore, this merging event this metallicity gradient, this internal metallicity gradient that this dwarf galaxy develops before the merger is actually responsible for a very complex chemodynamical signature in the Milky Way. And you can see the energy versus angular momentum space again. And what we notice is that the nuclear regions, the central regions in this simulation actually end up on low angular momentum orbits. These are the bright blue region here in this bottom panel, while the outer regions of this galaxy, the low metallicity portions of this galaxy, the outer regions actually end up on high orbital energy and high angular momentum after they are accreted by the Milky Way. So what we are doing is actually selecting. We might be biased towards higher or lower metallicities depending on our selection criteria. Nevertheless, this should not be as important because the fraction of stars towards high angular momentum regions in this energy versus angular momentum space is actually much smaller than the fraction of stars in the nuclear regions of the galaxy. So, but this is a caveat that I think it's important to mention. We can also, from this typical metallicity that we derive from the apogee survey, we can actually just plot this this galaxy in the stellar mass metallicity relation of local group dwarf galaxies. And we can actually utilize apogee not only to determine the metallicity of Gaia-Sausage, but we can also utilize data from apogee to also determine the metallicities for both the Magellanic Clouds as well as the Sagittarius dwarf spheroidal galaxy. And we can see that despite having a higher mass than the small Magellanic Cloud, this galaxy, this Gaia-Sausage galaxy, has a lower metallicity. And this is exactly what we would expect for a galaxy that had its star formation history interrupted from this catastrophic event. The catastrophic event being the accretion by the Milky Way. And in the bottom panel, I just show how we can utilize data from Gaia to select the stars from these dwarf galaxies. With the quality of the data that we have from Gaia as of now, we can select member stars from these dwarf galaxies quite easily nowadays. Okay, so now what about other chemical abundances? Because this is one of the main points, or one of the main questions that I asked a few slides ago. And we can see that in this magnesium over iron versus metallicity plane, again, we see that similar to the dwarf galaxies that we saw in the previous slide, this Gaia-Sausage population follows this declining sequence with the increasing metallicity in the magnesium over iron. This is just like we saw in the previous slides, that this is very characteristic of a simple chemical evolution history of a dwarf galaxy. And so, and not only that, but the magnesium over iron ratio of this population, of this Gaia-Sausage population here represented by the blue points, is below the magnesium over iron ratio from the thick disk at a similar metallicity. So this gives us a lot of confidence that we are not completely crazy regarding selecting this cohesive accreted, this accreted population within a bunch of stars mixed in the galactic halo of the Milky Way. And in order for us to kind of understand this chemical evolution trajectory here plotted in red, this is a very simple chemical evolution model, and this is represented here. And this chemical evolution model is represented in a different way in this star formation rate over time plot. And we can see that this chemical evolution, this simple chemical evolution with a declining magnesium over iron as a function of metallicity, as a function of increasing metallicity, is very characteristic. This continuous decline is very characteristic of a star formation history with a single peak of star formation, a single burst of star formation, if you may. And this is exactly, this model kind of can reproduce quite decently the behavior that we see for this dwarf galaxy. However, chemodynamical models with, just like I showed to you in the previous slide, will be desirable for us to understand the specific scatter in this chemical abundance plane as well. We can also look, this is another chemical abundance plane that is very, very interesting for us to look at. This is aluminum over iron as a function of metallicity. And one thing that we noticed, this was quite surprising to me, was that the stars from this dwarf galaxy, stars from this Gaia-Sausage dwarf galaxy, actually have higher aluminum abundances at a similar metallicity in comparison to the stars from both the small and the large Magellanic Cloud. This was pretty surprising to me. I was not expecting this behavior. And this behavior can actually be explained by a chemical evolution model with a lower star formation efficiency, as is shown by the dashed line in this figure. And this, I don't know exactly what this means yet. For instance, let's imagine, I could imagine like a star formation efficiency that is smaller in a low mass dark matter halo, for instance. because we have less, the gravitational potential is weaker and is not as efficient in collapsing the gas and transforming this gas in a galaxy into stars. But this is just speculations out of my mind. I don't know exactly what is the physical cause of this star formation efficiency being lower for the Magellanic Clouds in comparison to this Gaia-Sausage galaxy. Nevertheless, we can see that the metallicity distribution of this Gaia-Sausage galaxy, it is kind of truncated around FeOH of minus 0.7 around here, and this FeOH of minus 0.7 corresponds to a truncation of the star formation at around 3 gigayears after the beginning of star formation in this chemical evolution model. And well, this is kind of expected that there is this truncation of star formation because a catastrophic event happened in the history of this dwarf galaxy, which was the merging with the Milky Way. And now moving towards the globular clusters, this is again that figure that I showed to you a few slides ago, in which we have the classification of globular clusters within several accreted dwarf galaxies, and the green points represent the accreted globular clusters associated with the Gaia-Sausage galaxy. Among these globular clusters that people have classified as associated with the Gaia-Sausage, we can see that two of them are pretty massive. One of them is NGC 1851, and the other is Omega Centauri. Both of these globular clusters, they have been considered in the literature throughout many years in the literature to be candidates of nuclear star clusters, in particular Omega Centauri. So we can ask ourselves, among these globular clusters, in particular both of these two candidates, NGC 1851 and Omega Centauri, is any of them the actual nuclear star cluster of this disrupted dwarf galaxy of Gaia-Enceladus, of Gaia-Sausage? And one of the things that we can actually utilize to analyze the possibility that these globular clusters were actually nuclear star clusters of Gaia-Sausage is looking again at that simulation that I showed to you, in which we saw the metallicity gradient for Gaia-Sausage before the merger. And we saw in that simulation that the nuclear regions of the galaxy, the nuclear regions of Gaia-Sausage, after they merge with the Milky Way, they will end up on these low orbital energy regions of this plot. We can see from the bright blue colors. Well, if we expect the nuclear regions to end up on... Okay, sorry everyone. So I guess I was just talking about how the nuclear regions of this of Gaia-Sausage, prior to them, they end up on these low orbital energy regions in this energy versus angular momentum space, which is, well, given that the nuclear star cluster should reside within the nuclear regions of the galaxy, it would be kind of natural to expect the Omega Centauri to be a stronger candidate to be the nuclear star cluster of this accreted dwarf galaxy. So this is one of the evidence that we actually explore. However, there's another thing that we can actually do in order for us to decide which of these globular clusters are actually the nuclear star cluster of this galaxy, or if neither of them are the nuclear star cluster. So we can actually compare the mass of these globular clusters, which we know with pretty good precision thanks to Gaia, with the stellar mass of hosts of nuclear star clusters that we see in the local universe. And this is exactly what is shown in this figure. This is the relation between the mass of nuclear star clusters and the stellar mass of their host galaxies. This is all from a paper a review by Neumayer et al. 2020. And we can see that the mass of Omega Centauri, the predicted stellar mass for the host galaxy of Omega Centauri is well within the range of masses that we expect for Gaia-Sausage. On the other hand, the mass expected for NGC 1851, if these globular clusters truly is a nuclear star cluster, the mass predicted for its host galaxy is 100 times less massive than what we expect to be the mass of Gaia-Sausage. So following this line of argument, we actually we envision Omega Centauri as a much stronger candidate for the nuclear star cluster of Gaia-Sausage. And also, furthermore, if we consider that the Omega Centauri is not the nuclear star cluster of Gaia-Sausage, there is no other accretion event that happened throughout the history of the Milky Way that was between the Milky Way and a galaxy that is at least not even close to be as massive as the necessary to be the host of Omega Centauri. Despite they scatter in this relation, it will be very weird if another the host galaxy for Omega Centauri was any other accreted dwarf galaxy that we know in the Milky Way. Of course, the caveat is that this relation is calculated at redshift 0. So at redshift 2, which is the redshift of accretion of Gaia-Sausage, we don't know how this relationship changed. But nevertheless, this is what we have at the moment. And finally, we can actually utilize data from apogee from these globular clusters. The globular clusters of the Gaia-Sausage are shown here in this velocity plane. Again, you can see the sausage once again in this figure, and these are the globular clusters from Gaia-Sausage that actually have apogee data. We can actually utilize the metallicities from these globular clusters from apogee in order for us to determine the ages of these globular clusters from isochrone fitting, for instance, with a prior information of their metallicities. And in order for us to do that, we selected stars, members of these globular clusters, based on the distribution of proper motions from Gaia. And this is an exercise shown here for NGC 789, which is the blue point in this figure. In the figure to the left, you can see that stars associated with these globular clusters, the stars that have a higher membership probability to be associated with these globular clusters, have a very cohesive distribution in this proper motion space. And if we consider only stars with membership probability higher than a certain threshold, let's say 99.9%, we can see the color magnitude diagram of these globular clusters appearing in these Gaia bands. And then we can also utilize the distances to these globular clusters. This is a figure in this paper from 2021, which combines data from Gaia with data from the literature to derive very precise distances to galactic globular clusters. And we can actually combine this distance information with the metallicity information from apogee in order to provide priors to the determination of ages via, for instance, isochrone fitting. And this is exactly what we have done. And this is an example for a few of the globular clusters that we analyzed. We actually analyzed 8 globular clusters that are associated with Gaia-Sausage that have apogee data, and utilizing this apogee data, these apogee metallicities and the distances from Gaia as priors to the determination of the ages of these globular clusters via isochrone fitting. We can see that. Can you hear me?
Yes.
Yes.
Oh, okay. So my computer is kind of crashing again. But okay, we can utilize, what I was saying is that we can utilize this information as prior information to determine the ages of these globular clusters via isochrone fitting. And the ages that we get are very, very precise, like 0.4, 0.3 gigayear uncertainty in the age determination. So this is pretty good. And we can actually utilize this age, these ages which were determined with prior information for metallicities from apogee in order to recalculate or to determine the age-metallicity relation for the Gaia-Sausage galaxy. And in comparison, the literature, we had this age-metallicity relation, which was derived from a compilation of ages and metallicities, which are not determined in a homogeneous way. And this is the final age-metallicity relation that we get. You can see that this age-metallicity relation is very well constrained because of how precise both the metallicity and the age determinations are in our sample of globular clusters. So finally,
it's over.
no, I think my computer crashed again. I thought you were not hearing
Okay.
me.
I thought about it.
Your
Yeah.
advisor should buy a new computer for you.
Yeah, I should reinstall Ubuntu. That's what I should do.
But he is with a new computer.
Yeah, I need to reinstall Ubuntu. That's the problem.
I see.
Okay, what slide are you seeing?
56,
Yeah.
55.
Okay.
I think it's one before the last.
Okay, I think I'm back. Sorry, everyone. My computer apparently hates Google Meet. So before I conclude, before I leave you with my takeaway messages, I would like to thank the Galactic Archaeology group, or people that participated in this work, Professor Silvia, Angelis, which is now in Mexico, Stefano, which is now in Germany, Elio and Rafa as well. And these are the takeaway messages. I would like to leave these takeaway messages here, and I will be happy to answer your questions now. Thank you so much. You can contact me via my email or via Twitter as well.
Okay, Guilherme, thank you very much for this great talk. It was really clear, even though speaking for me is not my subject of study, but certainly I understand. I think I understand a lot of the subject. So thank you very much. So let's start with the questions. I will start with Reinaldo.
Hey, Guilherme. Thank you for the very nice talk. It was very clear. The results are very interesting, especially these last results that you showed. I have a bunch of questions here. If I have at least 3 minor questions for you. I'm very curious about what you mentioned. I think you were in slide 29, and you mentioned that it would be a necessary gas-rich merger to trigger star formation. But is it really necessary? Because as long as I think that there is enough gas in Milky Way, it would not be so necessary to have a lot of gas from.
It's not that it's necessary. It's just that in this one work that people analyze, what people eventually did was to look in cosmological hydrodynamical simulations for Milky Way analogs that contained some Gaia-Sausage analog in them. And what most of these works show, well, I think there is like 4 works doing this kind of exercise with different suits of cosmological simulations. All of them show that the progenitor of this Gaia-Sausage, but in these simulations, they are all gas-rich mergers.
Okay.
It's not that this is necessary, particularly necessary. I think the Milky Way had a bunch of gas as well, but it just
it's more efficient too.
It's just that such a massive galaxy, such as Gaia-Enceladus, probably had a lot of gas at the epoch of its merger with the Milky Way. So this is why I think there's this ubiquitous result that when people look for analogs in cosmological hydrodynamical simulations, they find these mergers to be gas-rich. I think this is
right. Right. Thank you. I have another question, if I can. From these simulations, I don't know if this Enceladus, if they put some halo of dark matter. I'd like to know if the simulations show what happens with this halo if they continue following this. I don't know, the resulting globular clusters or these stripes, or it's decouples somehow, or it's model dependence of the dark matter.
There is one paper that actually analyzed a pure any-body simulation that attempted at reconstructing in a lot of detail the merging of Gaia-Sausage, and I don't have a figure for that here, I think. But nevertheless, there is this one paper, and there's also this paper by Amarante 2022, which try to reconstruct the merger with anybody, but also accounting for star formation, with anybody simulations, but plus accounting for star formation. And they actually show exactly what happens with the dark matter. This other paper, I think one of the results was that 20% of the whole dark matter halo of the Milky Way actually was brought in by this merger. This I don't know exactly. So there is another paper. Actually, now that I think about it, there is another paper that came out a few weeks ago that they actually show that in this particular simulation, this any-body simulation, the resulting dark matter halo should be tilted to a certain degree, and this tilting of the dark matter halo would give rise to stellar overdensities in the halo. So this is kind of some of the results that they get from these pure any-body simulations, but yeah, that's what I know.
Thank you.
That people have tried to do in the literature.
Interesting to know. I was looking for this. It's really curious. And exactly about this figure, if I can make another question, I was curious also about this gradient, this metallicity gradient. Is it physically? It should happen because this I don't know, star formation is more efficient in the densest part of the of this galaxy. Okay,
that is likely what's happening. That is indeed likely what's happening. It's such like the bulge of the Milky Way has a higher metallicity than the disk of the Milky Way or the halo. So this is kind of what would be expected. This is just the natural evolution of a galaxy this mass at this certain redshift before the accretion event happens. And if this galaxy had this metallicity gradient, then, and it probably had, according to this simulation. And this is one thing that I don't know if cosmological simulations, these cosmological hydrodynamical simulations have resolution enough to resolve the metallicity gradients. But this particular work that worked with this N-body, this highly tailored simulation of this N-body plus N-body simulation that also accounts for star formation, this dwarf galaxy, as massive as the Gaia-Sausage is predicted to be, they naturally develop this metallicity gradient. And if this did happen, and it probably happened, it would cause like chaos into the chemodynamical signature of this galaxy in the Milky Way, which is exactly why I mentioned this caveat, because we are at a level that we know so much about how to reconstruct this kind of merging events, how to reconstruct these disrupted dwarf galaxies, that we can even speculate that if they had and care about if they had metallicity gradients. I think this is one of a nice message that we can extract.
Yeah. It's interesting. So because these elliptical galaxies, they're so hot, but the time scales, I guess, for the mixing of the material of more metals to go to the periphery, maybe it's too long to make the mixing, to homogenize this galaxy. Okay.
Yeah, definitely the star formation is not homogeneous. Like the chemical evolution models, the chemical evolution trajectories that I showed to you in this figure, they are under the assumption of instantaneous mixing of the gas. So, but unlike this chemical evolution model that I run, these chemodynamical simulations, they do not care about this instantaneous mixing. They can account for these metallicity variations or these variations in the chemical, the pace of the chemical enrichment across the galaxy. And this is exactly what they show.
Oh, thank you. Well, my last question, I think you already answered. It's at the time of the merger with Enceladus, it's probably Enceladus brought like it had 1/5 of the mass of the Milky Way in that time, or
yeah, the mass ratio was between 1 to 3 and 1 to 5, so it was
1 to 3.
Yeah.
Okay.
If you consider a major merger to be a mass ratio of 1 to 4, this was the last major merger experienced by the galaxy. So this is like the takeaway message.
Thank you, Guilherme.
Okay, see, I have several questions myself, and I will start with one that is concerning specifically this slide. I am really curious. I could not follow you when you were explaining about the star formation rates and how you compare and how you, because you said, yeah, it's clear that this event is a one single peak star formation rate, one single peak of those. So especially this graphic that you are showing here in the middle, in the top.
Okay, I see.
So how do you estimate the star formation rate? And can you explain a little bit these three regimes that we can see corresponding to the populations here in the right?
Sure. So the white model is a model that I run with because all of these chemical evolution trajectories I run with the same chemical evolution code, let's say, and this is just the standard Milky Way model that they suggest, and this is run. The difference between this model of the Milky Way to those of the accreted models that I say, or the models for the dwarf galaxies, is that this model for the Milky Way, it has a lot of, is much more massive, so it has a lot of gas in order to form stars. It also has a higher star formation efficiency, and a higher star formation efficiency because we, just like I said, we kind of, this is kind of this is kind of the interpretation that we can have, is that the dark matter halo of the galaxy, given that the Milky Way is much more massive, it has a deeper gravitational potential that is more efficient in collapsing the gas in order to form stars. So this is the difference. So it produces a lot more stars much quicker because it has a lot of gas, and it also has a higher star formation efficiency. Not only that, but another aspect of these models that is quite important is that given this deeper gravitational potential of the Milky Way model, when a supernova explodes, the gas enriched by the supernova will not be expelled out of the galaxy. It will be retained within the galaxy because of its deeper gravitational potential. And then it will be able to chemically enrich next generations of stars. So this is also an important aspect of this model, is this efficiency of the feedback of the supernova and how efficient they are in retaining the chemically enriched gas in order to form new generations of stars. So mostly these chemical evolution models are pretty simple, but this is the basic difference between them. And then the dashed line is just the same model as the red one, but with a smaller star formation efficiency. We were just checking if this behavior of these the surviving dwarf galaxies in comparison to the Gaia-Sausage, if they can be reproduced by any of the parameters that we were exploring. And the parameter that produces this difference in the aluminum abundance is the star formation efficiency, which can be translated into the total mass of these galaxies. Let's say, like, we can speculate that this is the case. So, and well, actually, this is not written in the paper, okay, but indeed, the dark matter halo predicted to be for this Gaia-Sausage galaxy, it truly is more massive than the dark matter halo of the Large Magellanic Cloud. And we also see this behavior in which the star formation efficiency for Gaia-Sausage is also higher than the star formation efficiency of the Large Magellanic Cloud. So perhaps this is indeed connected.
Okay, I understand. So, yes, I have to. I'm sorry, I have to reason very, very fast to see the connections. But yes, I think I get it. Thank you.
Yeah, the major point I think is that the star formation efficiency can explain the differences in aluminum abundances.
Yeah.
And the physical cause of this is not quite clear to me yet, and this is not written in the paper, but I speculate it has to do with the total mass of these galaxies.
Yeah, I understand. So you were saying that you think that this Omega Cen is actually a nuclear star cluster of the, well, that's your conclusion actually. I was wondering what type of stars are in this cluster?
All kinds of stars. I think I have a HR diagram for Omega Centauri right here. So you can see that this is the HR diagram for Omega Centauri produced in the same way that I showed to you in the presentation, and all kinds of stars. But the most important thing is that this globular cluster is considered to be the nuclear star clusters or the nuclear star clusters of an accreted dwarf galaxy, and has been considered as this since the 90s because it has multiple stellar populations, like perhaps 7 different stellar populations with a variety of different metallicities. So the stars within this globular cluster, they span a metallicity range from -2.5 to -0.5. So this is 2 decks in metallicity, in FeOH. So this is an insane difference in metallicity within the stars, within these globular clusters. And if we recall our fundamental astronomy classes, globular clusters are supposed to be these templates for simple stellar populations with a single chemical composition. So this is the reason why this Omega Centauri is considered for a long time to be the nuclear star cluster of an accreted dwarf galaxy. And the takeaway message that I would give to you is that there is the best candidate for the host galaxy of Omega Centauri is Gaia-Sausage.
Okay.
It's not the nuclear star cluster of Gaia-Sausage, it has to be Omega Centauri. It's just that it's the other way around. The best candidate for the host galaxy of Omega Centauri is Gaia-Sausage.
Yes, I understand. Yeah. So, what would you have? So what you mean is actually that you have these 7 different populations because of the origin of this cluster, not because it's just a normal cluster.
Yes, exactly. The formation of nuclear star clusters are completely different from globular clusters.
Yes, I understand. And would you expect some differences in because I guess in inside this cluster you also have some evolution and maybe some, because I guess the most massive stars are dead already. Because in 6-7 giga years.
Definitely.
So yeah, would you think this also contributed to these very large differences between the population metallicity?
That is a good question. I have no idea, because this depends on the model that you assume for the formation of these nuclear star clusters. If the nuclear star clusters are formed from, like, let's say, the fusion of two globular clusters, the two globular clusters crashing onto each other, and then you have multiple populations because of this because you have more than a single globular cluster together. This is one formation pathway for nuclear star clusters, which I don't think is the case for Omega Centauri, because of how massive Gaia-Sausage is. This formation pathway for nuclear star cluster is more common for low mass galaxies. But for high mass galaxies, which is kind of the Gaia-Sausage is kind of in the transition between low mass and the high mass regime. And for high mass galaxies, we have the continuous star formation because of gas falling onto this nuclear star cluster, the nuclear regions of the host galaxies, and forming subsequent generations of stars. So depending on that depends on the formation model for the nuclear star cluster that you assume.
Okay.
And we don't know which one is the case for Omega Centauri, because we don't know the host.
Exactly. Exactly, because you were trying to answer a question with another, we are the same question actually.
Yeah, we are trying to understand the host. This is the presentation that I showed to you is kind of small steps towards understanding the host, but we are still far way to go.
And I have I think I don't see any hands raised, but please interrupt me if somebody wants to ask, because I have another question concerning, I am really curious on where these dwarf galaxies come from. Like, okay, there was a Milky Way and there were dwarf galaxies. Like, where they come from? Like, they formed together with a group of galaxies, or they were just formed alone? I don't know.
I think the first thing that we assume is that these dwarf galaxies were formed independently in low mass dark matter halos, and then they fall into the Milky Way. However, there is definitely the possibility of a group of dwarf galaxies. For instance, Gaia-Sausage is, just like I said, is just as massive or perhaps more massive than the Large Magellanic Cloud. And the Large Magellanic Cloud is known to harbor a system of satellite galaxies itself. So it is possible that this Gaia-Sausage also brought in its own system of dwarf galaxies. But in order for us to disentangle this scenario, we are far away from that.
Yeah.
We can kind of speculate, but I don't know what we can even, I can't even imagine what we can do in order for us to disentangle the scenarios. A single dwarf galaxy or a system of dwarf galaxies being accreted at the same time.
I understand. Yes, that is really interesting actually, because this raises another question that where are the cousins of the Gaia-Enceladus? So
one way to go is that if we have more detailed models for more detailed anybody models, and we can confidently reproduce the final dynamical footprint of Gaia-Sausage into the Milky Way. We then can say, okay, so these regions of the for instance, energy angular momentum space that I showed to you several times. Let's find one of these plots. So if we know exactly the footprint of the Gaia-Sausage in this energy versus angular momentum, for instance, we could say, okay, so this region is populated by the debris of Gaia-Enceladus. So the debris of its satellite galaxies probably is somewhere around this. So, but we will need like simulations that also simulate Gaia-Sausage with systems of satellite galaxies. And then we will need to analyze in these simulations where the satellite galaxies end up in this energy versus angular momentum space or other dynamical spaces that we want to analyze. So this is kind of a difficult question, but I don't know, this would be one way to approach this, but honestly, we are far from that.
Yeah, I understand. Okay. Thank you very much, Guilherme. I know if somebody else has a question, want to answer. So if no, I have a suggestion to the name of the sausage. Maybe you can you can find the word for sausage in Greek, and then you can rename it like sausage in Greek. It's a suggestion.
Yeah, that is one possibility.
Yeah. Okay, so if there are no more questions, thank you, Guilherme, once more. Thank you. Yeah, applause. Thank you very much for this great talk. And okay, so if you want to say something before we end the transmission, Guilherme, please.
No, thank you so much. And I suggest everyone always watch the cycle of seminars.
Yeah, thank you very much. And Richard, por favor.
Bye, everybody. Thank you, Guy. It was great.